know what it's about, and then we can go into basically an unstructured discussion. Talk about whatever you want, and I'll explain as much or as little as everybody seems to want. So, essentially, Cassandra is an operational database that has a little bit of a different philosophy than a lot of the systems that we've used in the past. It has more in common with some of the techniques and algorithms that have been used in places like Google, Facebook. But where it's different is that it's based on, it's an open source project. So for DataStax, we have a product called DataStax Enterprise, which integrates Cassandra. We layer in some other technologies to make it a full stack. But it's really the core of it is Cassandra. The persistence is Cassandra. Where the philosophy is fundamentally what's different is that we keep all replicas in view and available to participate with all operations. And that seems like a simple point, but it has a lot of implications in terms of how your systems have to be designed to consider the availability of all replicas. So it's a tunable system with respect to CAP, so consistency, availability, and partition tolerance. And you can design your application so that you emphasize one part of that triangle and de-emphasize another part of it. And it's completely dynamic according to your design. So can I see a show of hands for who is familiar with Cassandra from previous experience? Okay, so quarter. Does anybody have any questions so far? Okay. So I'll do some diagramming if we need to kind of show visually how it works, but I'll explain a little first. In Cassandra, you have the ability to have multiple data centers inside of a single cluster. Clusters are where the data centers. Data centers each have, for each database, which we call a key space, a replication factor. And that's simply how many replicas you keep in that data center, in the overall cluster. You can store data in a geo-replicated way. You can have operations that are local to the data center or that involve multiple data centers. And you make these decisions based on your latency requirements, consistency requirements, and so forth. You'll often see a picture that looks like this when people are explaining Cassandra. Each circle is a node. And it represents two rings. Can everybody in the back see well enough? Come up if you need to see better. I'll get a different color marker too. So basically, the things that we would have to do in the past when we're distributing our data, what we often call coping mechanisms for DBAs. Cassandra's philosophy embraces those patterns and builds an engine to use those patterns directly. So we're just going to look at one data center here. This is a 4-node ring. And the idea of a ring is important because the ring represents how data is partitioned within the database. Partitioning, it's a common concept that you've dealt with, Hadoop and Spark, etc. We have it in Cassandra as well. Partitioning is handled automatically. We don't call it sharding anymore. Partitioning is something that is managed at the database layer. You have your normal data model, and again, within your data model, you have primary key. Primary key semantics still apply. Sense of uniqueness, ordering. But in Cassandra, there's a first component of the primary key called the partition key. And it can be simple or compound. But essentially is your hint to the database for how you want partitioning to be managed. This goes through something called the partitioner function, which is called the partitioner. to generate what is effectively a hash, just like you would see in a traditional sharding scenario. But that hash is the modulo, well, it's essentially a number. If you look at all the bits, interpret it as a long in Java parlance, you're going to get basically a sequence of bits that can be read as a number, and that number indexes into the ring somewhere. The ring determines which nodes own replicas for a piece of data. So let's say you have replication factor 2 in this example. In the simplest case, it's just demonstrating the replication. We have 2 nodes that own data. Neither one of them is a primary replica. They're both replicas. There's no implied importance of one over the other. And that philosophy is throughout Cassandra's design. There is no single point of failure, no preferred access path. The language of your consistency in terms of your operations is what defines how these get used in your operations. Most commonly, replication factor 3 is used. And that's used for a very specific reason, in that you can see more than half of the nodes for reads or writes, and at all times you have the availability of losing a node and still being able to see the majority of the nodes. So if any of you have read about consensus protocols and things like that, the majority of nodes actually has a pretty universal meaning here. So I'm going to cut right to an example of what we call immediate consistency. Whoever that was, bless you. But this is the kind of example I would normally show after explaining all the internals and demonstrating things for half a day. But we're going to cut right to it. We'll get some questions from it, I hope. Immediate consistency means that after you change your data, now, in Cassandra, let me frame it that way, in Cassandra, immediate consistency means that after you write your data and get back an acknowledgement that the operation was successful, you can read it immediately and see that state. So let's talk about a scenario with replication factor 3, where we write to an arbitrary set of 2 nodes. How many nodes would we need to read from in order to see consistency? With the default last right wins logic that's used in Cassandra, as long as you see one of the previous node's operations, you're always going to see the most recent operation. So any two of 3. That means if you couldn't get to this node for the write, and you can't get to this node for the read, you still see an overlap of the most recent change. That gives you immediate consistency semantics with availability. And this works because we have greater than here. Pigeonhole principle says you lose a node from the remaining nodes, the minimum number to get up to 2. So we say we write with 2 nodes and we read with 2 nodes. This many nodes we have an overlap. So now we see at least one of the most recent writes. And this is a common misconception about Cassandra. When people hear tunable consistency or eventual consistency, they're prone to make a lot of assumptions. And this is a great counterexample to show where tunable can actually help you have immediate consistency if you need it. This works better with odd replication factors. And the way you specify immediate consistency in this way is by saying, I want to use quorum, consistency level quorum. So to be clear, immediate consistency in Cassandra means consistency level quorum. Now, if you had replication factor 2, it doesn't work as well, and I'll tell you why. Replication factor greater than 3, odd is better. If you have 2 nodes, what's greater than half? 2 nodes. 2 nodes required at all times to see greater than half. When you only have 2 nodes, it means that if you lose a node, you can't complete the operation. You get back a response that says, I couldn't complete the operation, as if you had an availability problem in a single system image design. But by providing for greater than half to mean not all nodes, as in 3, and actually 4 and 5, and anything greater than that, you get availability and you get immediate consistency. So I'm going to pause here. I've kind of thrown some concepts out there. I want to know what questions we have so far. Fishing for questions.
Does that kind of like striping across drives?
No. So, RAID concepts are useful for demonstrating and explaining this. This is more like mirroring. So within each partition, the partitioning and the partitioner chooses where replicas are held, but each replica has the full partition. So if you think of a partition as, in terms of the storage engine view, just a row of data, the whole row is on every replica. Which means that the partition is the unit of replication. So if you, for example, stored all events for a particular user by partition, then you would have, with replication factor 3 full copies of that history. So sometimes people want to have partitions that are really wide, and you can do that, but there are practical limits in terms of performance. So generally you want to have some type of partitioning strategy that you use in the primary key that buckets those over time. So, for example, by year or by month. It would be better to have user events by user and month than it would be to have just user events, for example, because you could end up with an arbitrarily long partition that just keeps growing. More questions? All right, so I'm going to throw out some topics. We'll see what everyone's interested in talking about. Well, let's talk about eventual consistency. And then I'll throw out some topics. So eventual consistency is a topic that comes with certain assumptions. Eventual what? How fast is that? So there, if you look for it, there's a blog post out there that talks about the eventual consistency timing. When you write into a Cassandra cluster, the replicas that need to own the rights, the updates, changes, whatever, they all get the rights as long as they're available. If they're not, they get the rights later if you're within the handoff interval, meaning that another node accepted the operation on behalf of the node that's not available and will replay those changes in once it's available, up to a limit of time that you configure. But the point is that rights flow to replicas without hesitation, without exception, except for availability, and that's a temporary issue most of the time. So, the point of explaining that is that the way the consistency level works is it simply tells the server at which point in that propagation process you want to get an acknowledgement back saying that the operation was successful. So in the case of consistency level quorum with replication factor 3, that means 2 nodes have to have durably written the change before your client gets back an acknowledgement saying everything worked. The process of writing those changes to the nodes continues regardless. Cassandra is asynchronously pipelined throughout. Internally, it's basically an asynchronous system where different parts send messages And if they expect an acknowledgement back, it's built into the protocol between the different parts. It's not request response throughout. That gives a lot of flexibility to the designers about how they deal with replication. So even though writes will flow to all replicas by default, you don't have to wait for all the writes to get to all replicas. You can say, let me know when some fraction of them have completed. Like in this case of immediate consistency quorum. Reads are a little different. Reads, because you can specify quorum for reads. Reads don't need to see all of the replicas physically. They just need to see the number of replicas needed for the consistency level. That means it doesn't make much sense to tax the hardware to read all 3 replicas for a read. You just need to see 2. But what if the 2 you want to see, what if one of them isn't available? In that case, a Cassandra read will then retroactively involve the other replica. Normally, it doesn't have to route the request in a reactive way that way because changes that occur inside a Cassandra cluster are shared amongst all the nodes with a protocol called gossip. It means that availability information is propagated so that when a request comes in, it can be routed based on availability at the time. So going back to writes, going to all the replicas, if this replica is available, it's going here. If it's not, it'll be hinted and then replayed when the node is available. What does eventual consistency mean? Or consistency? It means that that doesn't happen synchronously in the view of your client if you don't want it to. That's all. Practical timing. The last time I looked at somebody's measurement of it, most of the time involved in propagation is wire time. So if you look at nodes within a data center, the 95th percentile is about 5 milliseconds, worst case. And a 2 or 3 year old data point that I read. If you wanted to measure the difference between consistency of getting replicas to a certain state, between quorum reads and all reads, or you could even do writes, you can measure it. Just write a certain number of rows with one consistency level, write the same rows with a different consistency level, and you'll see a very small margin of timing difference. It's not seconds or anything like that, it's milliseconds. Now, topics. Do we have any more questions based on that? All right. So, topics. We can talk about how Cassandra is used with different use cases and scenarios, what people do with it. We can talk about operational trade-offs and management strategies. We can talk about how people are using it with other tools like Spark, for example. Any of that sound interesting? Use cases. All right, use cases, that's a good one. Event data is a great example. Anything that's time series is obviously, we can think of it in terms of event data. Anything that requires quick access. Anything that is essentially accumulating lots of data over time and you need to be able to access it quickly. So we deal with web apps a lot, we deal with mobile apps, we deal with logging, we deal with IoT. Essentially, any problem domain where you need to have high availability, good performance, and linear scalability, it's a workable use case. But we really look at time series, event data, and IoT as the kind of the wheelhouse. And that's changing as we go forward. The platform is getting better in terms of the kinds of operational workloads it's good at. And, a lot of the systems out there are too as well. But essentially, Cassandra it's focused on the philosophy of denormalized data structures. So It's not strictly a key value store. It's not a tabular store. It's a hybrid. It's columnar, but it's also dynamic in structure. And I'll explain that in a little more detail here. Somebody mentioned that Cassandra is unstructured. So that's an important topic to touch on. Inside a Cassandra row, you can have arbitrary row structure if you like. That was the initial design based on thrift. I'm sure that you've seen thrift and used it in some places, but thrift comes with its own prescription on how to build your server. It also comes with certain inherent limitations in terms of structure for the definition of language and serialization and deserialization. So Cassandra, modern Cassandra uses its own binary protocol that is a lot more flexible than thrift. It also implements its own internal server logic that doesn't depend on the thrift RPCs. So what that means is they were able to enhance the design, especially going forward in Cassandra 3, they were able to make changes to the way that the internal asynchronous threading works, the messaging between the threads, so that it's much more performant. But there's also an evolution in terms of structure. I built my first system on Cassandra using the dynamic layout, using the ability to have different structure on a per row basis if I wanted. But when you think about it, really, that contextual interpretation of your structure has a certain amount of mental baggage that goes with it. Somewhere, the intelligence has to exist to know what the supposed structure is, what the required structure is, what are the variations, and how to deal with them. So having a fully dynamic structure is, from a design perspective, it's a nice idea. But in practice, you often want to have some structure. So I'm not going to tell you want rigid structure everywhere or complete unstructured systems. I'm going to say that each design has a measure of structuredness that you want in your data model. And picking where that is part of the art of designing a data model. In practice, defining a structure with the semantics of a tabular layout is usually what people are after. Even if, through clustering, we provide some dynamicism in that structure, and I'll explain that a little bit. So, I left out a part of the primary key here. I left out the clustering. So we can have clustering that's simple or hierarchical. In your primary key in Cassandra, you get to specify the partitioning structure, the division of partitions by composite partition key. Unless I turn my head left or go away from the mic. Sorry. But you also get to specify the internal, the minor ordering on a hierarchical basis. You get to say that within a partition, within a wide row, I'm going to have a tree of data. I'm going to have ranges of data that I can efficiently access. I can go from a particular point in the partition by name of a field or value of a field, and I can efficiently read all of the rows from that to some other point in the partition. And that's where you get a nice combination of some structuredness in the data model, plus the good things that come with the ability to control the clustering of data for access. So the most performant data model you can get with Cassandra is one that gives you direct addressability of ranged reads, unless you're just doing specifically in rows by equals.
You mentioned ranged reads, and you also mentioned time series. Within, I certainly know Oracle HR, you have what's called date tracked queries, and conceptually it's actually quite simple, but in actual doing it's a lot more complicated. If you had something where you said, okay, I've got a record and from this date to this date, it's considered the current record. So it's from now until some unknown future date. Then I say, okay, I've got a second version of this record, something changed. And even though that previous record is still, I'd say end date one record, take the next start date and future date that. Now, both records are equally as valid. It all depends upon the query that says when I'm interested in the data. Is that something that is actually easier to do in Cassandra? Or is that something that's more probably the domain of a traditional relational database?
So what I hear, let me restate the question and make sure I understand it completely. You're talking about what you consider two different query patterns against a set of data that is time series data, but also has revisions. And you might want to ask the database for, in your where clause, you might say first by time or time range, and then by revision, or you might say first by revision and then time range. Do you
No, more like where the date that I'm interested in falls between the beginning and end dates of something.
So if we set aside the revision aspect of that for a moment, the date part is really easy. Cassandra supports time UID and date time, and basically any data type that gives you ordering, which they pretty much all do, can be used as a marker for a range of values. So if you just use a timestamp, let's assume, for the sake of simplicity, that your timestamps are all you need.
It gets a lot more complex than that. If you're dealing with one or two tables, it's really easy. Now take it out to 20 tables, and now you've got a problem.
So there's another aspect of that we want to talk about. So dealing with time series data in Cassandra is very easy. Dealing with views that have different query structures is also easy. The fastest performance is always going to be by using query tables, which means you model this whole primary key based on your query structure in order for the clustering as well. But there are other tools that you can use to get decent performance, depending on the kinds of access methods. So direct Cassandra structure and query tables, fast. If you use secondary indexes, it's not going to be as fast. It's not going to scale as well because it's a fan. It's basically a mini MapReduce. It's just highly specialized. The other tools, like in Cassandra 3, we have something called materialized views. It's a little bit of a loaded phrase because it has such baggage with it from other systems, but it does allow you to define other orderings in the primary key and field components that you want to include in other named views. So you write once, the other views get updated. In terms of just addressing ranges of reads and a series of rows, 90% of understanding how to build a Cassandra data model is understanding how to design a primary key. That's what gives you the constraints around the queries that are supported for that data model. Partition values must be specified, of course, because you can't introspect every node magically and know which ones to include without generating the hash. So you must specify every component of a partition key for all queries that are in any way partition specific. I'll tell you what the asterisk is on that in a minute. But your clustering determines your major and minor order within the partition from that point forward. And it's not that you couldn't ask arbitrarily hard questions that would actually end up yielding analytics load. But in general, the query language for Cassandra, CQL, emphasizes access patterns and patterns that are scalable. So that means within this, if we had a row structure, we're looking in, say, the partition X, Y, and Z, not to Z. And then within that partition, let's say we have a text to type in our partition key. And then we have a text, this is bar card, text type within the first clustering component. That means that this partition is going to have what you might consider some logical rows within the line partition. We're going to have a separate row and fields for every unique value of the clustering. So text, let's call this partition name food, text, cluster name is bar. So this internal record in the y partition would be bar equals, let's just say blue,